Next talk is by Alejandro de la Vega from UT Austin. He's going to talk about Neuroscout, a cloud-based platform for flexible reanalysis of naturalistic fMRI datasets.
Thank you. So let's just jump straight in. So I'd like to start out by actually thanking everybody. I think we've actually had great success with open science, and in large part the whole neuroscience community. We have diverse open naturalistic datasets among many other big datasets available. So just as an example, these 6 datasets are available either on OpenNeuro or on DataLad or another website, but they have the complete data. They're in bits format, so you can pre-process it easily. They have the stimuli associated with it, so you can actually do some work on the stimuli. So this is like really big step to actually understanding how the brain works under naturalistic cognition. So round of applause for everybody, really. But more data, more problems, really, because complexity introduces a whole set of new challenges, which I think resonates a lot with the last talk. So naturalistic data in particular has the challenge of being really difficult to annotate. So if you want to understand something, the time course of a feature across a movie, you'd have to sit there, usually and manually encode it, which is fine. People have done that in science. For some features, you need to do that. But it's also inherently limited just because it simply does not scale. And in general, as you obviously well know, fMRI reanalysis is very resource intensive, which is fine if it's your own data set, you're willing to sink a couple months into analysis, but this sort of discourages the export to reuse of valuable data. So what we really need are tools that make it easier to quickly gain knowledge from these really valuable data sets that honestly cost millions of dollars to collect. So how can we get the most out of them? And like I said, you really want it to be scalable because as is now, it's prohibitive to really replicate analysis across data sets. So we can't really test the generalizability of our findings across data sets, which is what we'd really like to do if we want to learn something about how the brain works. So how can we really harness these awesome naturalistic data sets that we have available? So the first step towards that is automated annotation. So to really maximize this utility, we need many psychologically relevant features. We don't just need the one that we care about. One of those reasons is because we need to control for confounds. And another reason is because we might want to test like how generalizable the effect is to that specific variable as opposed to just more general effects. So we really want to understand as much of the variation, capture as much of the variation going on in these complex stimuli. To this end, we've developed a library called Pliers, which is a Python library for feature extraction. And what Pliers basically does is it harnesses the power of machine learning algorithms and content analysis services which exist, such as Google Cloud Platform, Clarify, and IBM Watson, to automatically extract hundreds of features at once from a stimulus. So what you can do is you can extract visual features such as faces, you can label scenes, you can get some low-level variables such as brightness, vibrance, or in the auditory domain, loudness for your transforms. You can also automatically transcribe the audio. You can force align a transcript you might already have. You can add lexical norms, etc. So basically, it makes it really easy to get potentially interesting variables out of your stimuli. That's great. So does it work? So we don't have any sound here. But this is actually a clip from the HCP data. And on the top right, you'll see automatically extracted image tags from Clarify, which basically get at what's going on in the movie. In the movie, you'll see people's faces outlined with a box.
You walk out and you see everybody.
Here we have an automatically extracted transcript from IBM Watson. And on the bottom right, we have automatically encoded lexical norms from that audio.
This is a good place for people to raise a family.
As
you drive through Bridgeville, you can feel that you're in Americana.
So what I really wanted to show with this clip is that there's a lot of information in these movies, and it's not easy to capture them, but Pliers lets you do that in a way that's actually scalable. So that's great. That's the first step, to get a lot of features. But then there's the second part, which is that the reanalysis is still going to be really difficult. So even if you get those features, you might still be sinking, at the minimum, a few months into analysis, at minimum, a few weeks, right? So to really solve this problem, we're introducing Neuroscout.org. And so this is something we're introducing officially as an alpha, so I'll give you the link later, you can play with it. But it's an end-to-end platform for the rapid and flexible reanalysis of fMRI data, but with a specific focus on naturalistic data. So instead of me talking, let me show you. Here's Neuroscout. You can essentially use this analysis creator to build your analysis. Here I'm going to do automated face detection in raters. I'm going to select the task, the runs, and then I'm going to save it, which gives me a unique identifying number. Then we can search from the predictors that we've already extracted for you. So here we have a couple hundred, and I can whittle it down to face detection confidence, which is from the Google Vision API. And then I can, of course, search for fMRI prep, which will give me a lot of confounds that I need to include. So here I'm going to just select 6, the rigid body transforms for fMRI prep, but I could select whatever I wanted. I can review which predictors I have. And now I can manipulate them. So obviously, you normally need to scale, orthogonalize, threshold these variables. You can do this in a way that's standardized, and instead of a random script you might write, it's in a way that's standardized. Then we can convolve our variable of interest with href. And finally, we can define some contrast. So here, we're just going to do the easy thing, which makes a 1-0 contract for the variable that we're interested in. And then you're going to sit there, wait, hopefully not too long, and get a design report. So let's take a look at that. So this is the automated reports that are generated by Neuroscout. You can see the design matrix. You can click on any of the variables and look at the time course of that feature. So for example, here is where faces are present in the Raiders movie in one run. And then you can look at the correlation matrix. So you can actually examine and decide, is this a valid analysis? Is this like a valid fMRI analysis, just like you would any time? You can review it, and once you're happy with it, you can say, okay, I agree to our ominous terms, and I'm going to submit this analysis. So this is submitted for generation, and then comes execution. So this will take a little bit, because everything has to be compiled into a self-contained bundle. But once that happens, you get a screen like this. So your analysis is passed. Congratulations, you can run it. Then you get this command. So this is a command to run the Neuroscout CLI. And as you can see, this is your unique ID, which is the most important thing. But what this command will do is it will download the Neuroscout image, and thanks to NeuroDebian and Docker, we can, without worrying about downloading software, without worrying about downloading data, and thanks to DataLad, we have an automated bundle, which includes the links to the fMRI data that's pre-processed, the statistical model in bitstats model, which is a standard way to codify that model, and we have the actual predictors. This is fed into Fitlins, which a couple of us have been working on to create a standardized bids app for fitting statistical models using NiStats, PyBids, and NiPipe. And once the results are fitted, the results are automatically uploaded to NeuroVault, so you can actually share them with your colleagues. So this is great, but does it result in something reasonable? So first, let's start out with the easiest thing, so speech. So this is basically just time-locked speech on-off across the movies. And in the 4 data sets that we have, the transcripts, we get exactly what you expect. We get activity in auditory areas and speech perception areas. So that's great. I would hope to see that. But I think it's also remarkable like how similar the results are across these data sets, even though they're actually quite different. For example, in the case of the OHBM, that's a developmental data set. Now let's look at something that maybe you also already had a strong a priori hypothesis for, but maybe would have been a little bit harder to test, and this is buildings, so like houses essentially. So this is a feature from Clarify, which automatically tags images with whether or not it thinks it has a building. And as you can see, in all the data sets, you're getting very similar patterns, and in most of them, especially these 4, you're getting pretty strong activity in parahippocampal gyrus. So that's great. I think that's what most people would expect. So good. So let's move on to something that maybe you also had strong a priori hypothesis for, but the results are a little different. So this is faces from Google Vision. And in these 3 data sets in particular, we get what you'd expect. You get FFA, right? So great. But actually, it's not that simple because you're actually getting a lot of other stuff, right? So what's going on? We're not quite there to be able to control for everything, but this is an example of something that in naturalistic data might be harder to study than we thought. So if you look at the brain, there's a lot of stuff going on. FFA was actually quite difficult to find, but across all the data sets that we have, we got very robust results. It's actually one of the most consistent contrasts across all these different data sets. So what we hope the Neuroscout will enable is for people to actually investigate, is this because there's more going on in face activity than we thought, or is there some stuff we need to control for that's like covariating with face activity during movie presentation. And finally, something that maybe you wouldn't have studied, but because it was easy, you're like, hey, why not? So this is shot change. So this is every time there's a major pan in the movie, it is labeled automatically by Google Vision Intelligence. And as you can see, you get really consistent results that I think are theoretically valid, or at least make sense to some extent, which you get activity in visual cortex, precuneus, and superior parietal cortex. So I think it's a really nice example of how Neuroscout might enable people to test new questions that otherwise would be maybe inconvenient to test, so you would never even bother to ask them, but you can discover something new. So just to summarize, Neuroscout is a tool to platform for fMRI analysis. It's user-friendly, easy to use. It's reproducible because there's a self-contained bundle with a unique ID that you can always fetch. It's scalable and generalizable, so you can test across different data sets. Incentivizes exploratory data reuse, so we can take advantage of those awesome data sets that we have. And I think really importantly, it's also continuously improving. So obviously, there are significant issues with some of the automated extractors. They're not perfect. But I think maybe most of us have noticed Google's getting scary good every year. So this is only going to continue to improve. And of course, thanks to the community at large, we get more and more data sets every year. So go ahead and try it. Here's a link. It's ready for public consumption and breakage. Hopefully not, but potentially. And finally, I'd like to just end by saying this is truly a collaborative effort. This is really a great example of like how all the tools in the neuroscientific, neuroinformatics community have come together to build a cool platform. But it's really, based on the work of a lot of other people, and of course, all the labs that have shared their data openly. So thank you, and please check it out.